All right, this is another one on equivalence relations. We're given two equivalence relations, R and S, on a set A, okay? And we want to prove that the intersection of these two equivalence relations is also an equivalence relation. So we need to show that R intersection S is reflexive, symmetric, and transitive. Okay? So let's see reflexivity. In other words, we want to show that X is related to X for every X. So X is related to X. So this is not a nice notation. I'm going to write XX is an element of the relation R intersection S. This is what I would be using. It's kind of long and ugly notation. Okay? For each X, we need to show that XX is related to, is an element of the intersection R intersection S relation. Okay? All right, let's see. So let X be a generic element in A. Okay? Since R is reflexive, then XX must be in R. Also S is reflexive. Why is that? Because we assumed R and S are equivalence relations. Okay? Since S is reflexive, XX is in the relation R. So these two together imply that in the relation S. These two imply that XX is an element of R intersection S. Hence, every generic element X is related to itself in this intersection relation. So hence R intersection S is reflexive. All right, the second one we want to show is R intersection S is symmetric. So we're going to suppose that XY is in this relation, and we will show that XY is, so we want to show that XY is Y-axis in the relation R intersection S. Since XY is in the relation R intersection S, this means that XY is in R and XY is in S. Also, since R is reflexive, symmetric, this means that XY is in R implies that YX must be in R. Also, since S is symmetric, and that XY is in S, we have that YX must be in S. So therefore YX is in R intersection S. Hence R intersection S is symmetric. The third one is to show that R intersection S is transitive. Well, suppose XY and YZ are both in R intersection S. Well, this means that XY and YZ is in R, and XY and YZ are in S. But R is reflexive, transitive, so XZ. So XZ is in R and XZ is in S. Hence, XZ is in R intersection S. Then R intersection S is transitive. Therefore, from 1, 2, and 3, R intersection S is an equivalence relation. One quick note here, the intersection of two equivalence relations is an equivalence relation. That's what we have proved. But the union of two equivalence relations may not be an equivalence relation.